we were looking at a basic circuit. A basic circuit, probably 99% of the basic circuits. So we say a circuit has to have, it's got to have some type of voltage to it, right? And then it's got to have conductors, and then it's got to have a load. But probably 99% of the basic circuits adds another element called some type of control device to actually control the flow of the current. Of course, here we're actually using a switch. This is basically what a control circuit. So in this class, we'll call these circuits control circuits because that their predominant use in industry is to control something, right? Usually some type of actuator. And we went over there to the manufacturing lines and actually saw some of this come into play. So we have all these devices that comes into play that either are going to close a circuit or open the circuit. Of course, a light switch, you do it manually, right? But then we got all these things called sensors that takes physical quantities and converts them over to electrical quantities for us. You saw a bunch of sensors in there. And all they are just these switches like this. But instead of me having to go over there and flip them, right? You understand that this is done by some other physical means, by pressure, by light, by sound, by magnetics, by all different types of features. There's really literally almost nothing that we can't electrically sense. Equilibrium, so we got gyroscopes and stuff like that. You can see that now, you can take your cell phone and do what? Flip it around. And what's sensing that so you got a sensor in there that's actually sensing what? The motion, right? So it's really neat what we can sense now. This doesn't do justice to control devices. About the only one they have. And we teach class in sensors. They're so important as far as automated manufacturing goes. In this class, you just kind of see them over there on the manufacturing line. So we have sensors that sense level, they can sense height, they can sense pressure, they can sense force, they can sense distance, they can sense proximity, they can sense, like I said, equilibrium or where you're at in space. They can do all kinds of stuff. We have two forms. We have what we call digital sensors, and which I think the book describes as discrete sensors. So these are the sensors that act just like switches. They're either what? They're either off or on. And then we have what we call analog sensors because we don't live in a digital world. We live predominantly in an analog world. So if I want to sense the amount of pressure, then we can't use a digital sensor, right? You understand? If I wanted to sense the temperature, I can't use a digital sensor. If I wanted to sense the amount of light or the amount of force, then I can't use a digital sensor. So we have what we call analog sensors. So analog sensors, analog is a term on something that completely continuously varies over basically an infinite range. And I think the analogy that we used, if you got a light dimmer switch in your house, that's an analog sensor, right? Does that make sense? The volume control on your TV would be what? Analog, right? So we have to have these analog devices. But unfortunately, computers don't understand analog. They understand a technique called digital. So what we have is we have these special circuits that we call analog to digital converters. And what they do is they take an analog value and convert it over to a digital number for you. And the digital number actually represents the weight of the number. And then once I've got it in digital form, then what can my computer do? My computer can process it. And if I'm going to output an analog, if I want to control an analog device, like the speed of a motor, then we have digital to analog converters, where the computer or the PLC can actually develop a binary number, store it into that analog, that digital analog converter, and it outputs an equivalent analog value to control the speed of the motors, control temperatures and stuff like that. The only sensor I have up here in this old picture is that little float sensor right there. And y'all know what float sensors do. If you got a commode in your house, you got a float sensor, probably. Symbols of the trade. These are not our symbols. Some of them are. These are your voltage sources. This is a symbol for an AC voltage source, and this is a symbol for a DC voltage source. A lot of people say the battery, which was originally the sources that we had for DC, but now this symbol right here represents all DC sources, whether it's electronic or whether it's actually a true battery. By the way, if we see any of these symbols and we draw a bar through it, an arrow through it, what that means is that it's adjustable. But you can ask almost anybody, even in the trade, and they'll ask you what this symbol is for, and they'll say a battery. But if we come over here on any of these symbols, except for the wire, and if they put an arrow through it like that, that means it's adjustable. So if you take like DC or those courses like that, those power supplies are what we call variable power supplies, which means you can do what? You can adjust them over range. So we have variable resistors, we have variable AC supplies, we have variable transformers too, which we don't use much in trade. This symbol right here is what we refer to as ground. Okay. And this is probably one of the most misused symbols in the trade, because ground means ground. So electrical power is trying to get back to earth ground. And so this is the symbol for earth ground. Okay, y'all understand that? This is the symbol right here for electrical common. So my cell phone does not use a ground. It's got a what? A common. But you'll find out just about everybody calls a common a what? A ground. So you go out there on your car, huh? It is. This is the return. That's what it is. Of course, you got to understand AC. The return is doing what? Yeah, swapping. So in AC, we refer to it as a neutral. And it is the reference for our circuit. So usually we have a lead, what electricians call hot and neutral. If you ever been in the electrical trade, you say hot and neutral. And neutral, we can't say it's the return. Why? Because AC is constantly swapping, but it's the common reference point. So every circuit has a common reference point. And if you look at the National Electrical Code, they don't use the term hot and neutral. They use the term ungrounded current carrying conductor, and they use a grounded current carrying conductor. That's the two terms they use in NEC. So hot and neutral are trade names. And of course, this is a symbol for a fuse. I don't have a symbol for a circuit breaker up here. A symbol for a circuit breaker is just two dots, and then it's got a little hook that goes like that. And we talked a little bit about a circuit breaker. A big advantage of a circuit breaker, of course, is we can reset it if we have overcurrent. If you have overcurrent, it blows. You got to swap it out. The advantage of fuses, they're a lot cheaper per amp, per volt. These overcurrent protection, they fall into a category called overcurrent protection devices. And they're rated in two things. They're rated in how much current they'll handle through them before they trip or pop or blow. And then the other thing they're rated in is how much voltage they can break. So if you ever look at these overcurrent protection devices, they should have two ratings on them. So you wouldn't take a circuit breaker that's rated for a car that's rated at 14 volts and put it in your house where you've got 120 volts worth of push. Because it could literally do what? When it tries to open, it could literally arc across and continue conducting. Anytime we create an arc, it creates a gas called ozone. So air itself has a really high resistance. You can look at that. You can take your ohm meter and hold it up in the air, and it's going to show you an overload. So it's got so much resistance that we cannot measure. Right? You understand that? But the problem is, if I create an arc, it creates a gas called ozone. and ozone has very low resistance. So anytime we create an arc, we can have problems because that arc can keep what? Conducting even when we're trying to open the circuit. So we take, and that's one big advantage that AC has over DC, is AC has a tendency to self-extinguish because it drops to 0 volts. So when it changes direction, it literally drops to 0 volts. If it drops to 0 volts, we have no push. So AC is considered to be self-extinguishing. DC, we have to do things to try to prevent them from arcing. We break contacts extremely fast, or we put a special circuit on it called stubber circuits and stuff like that. These are the symbols that we're going to be using in our trade. Now, so these are electrical control devices. So there it is. There's a symbol for a circuit breaker. Nothing but a circle is the symbol for a relay coil. So relays consist of two things. They consist of, and we pass these around, right? You understand? They have that coil of wire, and we call that a coil. And then we have the contacts that are controlled by that coil. The coil itself has this symbol right here. It's nothing but a circle. And then we got the symbol right beside it. What's that a symbol for? A light bulb, or in the trade they call it a luminary. Then we have push buttons. We have what we call normally open push buttons and normally closed push buttons, if that makes sense. So normally open, if I had it hooked up to a light, every time I pressed it, the light would come on. Normally closed, the light would be on, and every time I pressed it, the light would come off. Now, this is kind of misleading. These are what we call momentary contact push buttons. So I should rephrase that. Momentary contact means that you force it into one position, and when you let it go, it automatically does. It goes back to its non-normal position. Now, when we get into relay contacts, these are the contacts that are being controlled by that coil. We have two types of relay contacts. We have normally open contacts, and we have normally closed contacts. Y'all see the difference in the symbols. Okay. So a normally open contact does not have the bar through it, or the line through it. The normally closed contact does. So what does that mean? Well, that means on this first one, if I don't have voltage across that coil, and this is in series with my light, so let's look how we would do this. So I'm going to come up here. So what we need to do, let's see what I got by this. I'm going to go back. And I'm going to deliberately insert a slide right here. So how many wires do we have to have? 2. Well, notice in electronics, we kind of do it kind of different. Notice we draw our wires across the top. What we do in controls is we draw our 2 power lines, we draw them vertical. Where did I insert my slide at? Down here somewhere. There. So in controls and also in PLCs, because this is just a form of using the same format, what we do is we put our 2 power lines, we do them vertical. So those are my 2 power lines. And generically, we refer to this as L1 and L2. Now, we consider L2 to be either the ground or the neutral, or the common or the neutral, whichever. Sorry. And then what we do is we connect circuits. We put a dot right here. And then we come over here and we connect the circuit. So let's say I come over and connect this circuit. So that's a symbol for a momentary contact, normally open push button. And then I'm going to come over here and I'm going to put this. This is a symbol for a relay coil. And then I'm going to come over here and put a dot there. Now we're going to end up with a lot of relays. And we're going to have a lot of coils. So what we do is we name these things. And we give them what we call we give them a logical name. So I might call this like CR. Now normally, just generically speaking, they put the names in the center, but if you ever look at a industrial printer, the names get pretty long and they usually write the names of the coil down at the bottom. Huh? Industrial control printer. I'll show you one. I'll show you one we got from this deal. Then I'm going to come down here and I'm going to put this. And then I'm going to come over here and I'm going to put a light bulb. So we got two single element series circuits. Now we're going to have hundreds of contacts. So what I do under this contact is I come up here and put the same name that controls the contact. I put that name, I associate that with the contact. I mean, the same name of the coil, which is controlled in the contact, I give that contact the same name. So how would this work? So right now, there's no power across the coil. The coil's de-energized. The normally open contact would be open, and so the light would be off. I come up here and press that button, that's going to energize the relay. That normally open contact is going to do what? It's going to close and the light will come on. Now what does this look like? Well, this looks like a ladder. And what do we call the individual steps of the ladder? A rung. So what do you think we call these? We call these rungs. And we call this ladder. We call these a ladder diagram, or we call it ladder logic. And this is what a PLC programs. It says what's going to happen is that CR could or could not be real. It could be a soft core, which means it's done by a computer. It's not a real thing. Does that make sense? Which is pretty neat. And we talked about that. And when we get into complicated control circuits, probably 90% of the control circuit is just making decisions on when things happen. Well, what we can do is all that decision making, we can do what? We can represent that in a computer. But what we would like to do is we'd like to create a high level language that people that work in the electrical trade understand. So anybody in the electrical trade, in electrical controls, not house wiring, anybody in electrical controls understands ladder diagrams. Ladder diagrams have been around for years. So it would make sense when they came up with a programming language for a computer that they would use the trade, the technique that's used in the trade anyway. So one of the predominant programming languages in computer in PLCs is ladder, and that's what we're going to teach. Now they're basically four. One of them's called a function block diagram, which uses more like a flow chart that you run into in computers. And then we have several languages that are neat, and they do better code, but they're not what most people use. So this is the predominant language in PLCs, it's ladder. You'd have to be way up there before you moved over to those other languages. So we don't have lights inside the PLC, but and we'll look at that later on. So what we do in the PLC is we program using ladder logic. And that's what we're going to use in this class, ladder. Okay, this makes sense? And of course a parallel circuit would look like something like this. So I could come over here, and then I can come over here and put this. And then if it belongs to CR, I'd put that. Then I would come over here, and then I might put one, let's just use lights right now, right here. And then I would tap off right there, and I'd come down here and I'd put another light right there. And then I'd tap off right here and put another light right there. And how far can we go? We can go a long way. This is a parallel circuit. So the only circuits we have in controls is we have single element series circuits. There's no such things in controls as two loads in a line. We can have multiple. So this is a line, by the way. So this is one line, this is the other line, and this is another line. So the wires that move, when I draw it, the wires that move horizontal, we call these lines. And rule is one load per line. But we can have multiple loads per rung. right? You understand. But if I have multiple loads per rung, then what that means is that's a parallel circuit. And I can come in here, guys, and I can put all kind of control devices. I can hook them in series, I can hook them in parallel, and that does not make it a series circuit. And the way you hook control devices does not make it a series circuit, and it does not make it a parallel circuit. What makes it a series and a parallel circuit is how you connect the loads. So I could come over here and I could put another contact right there. I could come over here and put a push button right there. This is not a series parallel circuit. This is a parallel circuit. So we can connect control devices. We can connect them in series. We can connect them in parallel. We can connect them in series parallel. That does not determine what type of circuit it is. What determines the type of circuit? How the loads are connected. And in PLCs and motor controls, we only have two types. We have single load series circuits and we have parallel circuits. Now, when you get into electronics, you'll run into series parallel circuits. But in control circuits, we only got two types of circuits we're going to worry about. So this would be made up of 3 rungs. So this would be a rung. This would be a rung. Oops, sorry, I'm going to spell it right. And this right here would be 1 rung. And people get that confused. So 1 rung, no matter if it's parallel or series, is 1 circuit. It's 1 circuit. So in PLCs, it's 1 circuit that runs between L1 and L2. That would be considered to be a rung. Everybody okay? The programming software we're going to use is something called RS Logix. And we're using the 500 version series of that. No. No. These costs, to license this software, if you're not an educational institution, it's thousands of dollars. No, what comes with the book is a version called Logic Pro. You don't use it to program a PLC, but it emulates a PLC. Now that, you can license that for maybe, I think it's $15 for a 5-year license. $15 for a permanent license, I think, but they only support updates for 5 years. But that would be a really good technique just to play around with it. You can't upload it from a PLC. You can't download it to a PLC, but it's an emulation. So we'll be using that a lot in this class. The version that you have, I think you have to have, if it's still in the book. Is it still in the book? Oh, thank goodness.
What about it? When you put it in your computer, it's just giving you like a practice run.
Yeah, you can't print anything with it. And I'll show you. We're going to use that a lot in this class because I don't have to have a PLC in here to show y'all a program. And then we can emulate things, which is really, really neat. So let me show you RS Logic. So this is what I'm going to do is open a program. So this is a PLC program. So notice it has 2 lines. This would be L1, this would be L2, and then the circuits are made between wires. Now, of course, you won't get into it. We'll get into timers. So this is a timer. Where you put the timer down. Well, at certain times. One of the big problems that people don't understand is anything that's, most of y'all do that, but anything that's at rest wants to do what? Stay at rest, and anything in motion wants to stay in motion. So when you start your car, you're sitting at a red light and you start off, you have to push the gas pedal way down because you have to overcome the energy, all that work. But as soon as you get up to speed, what do? You let off. Well, when you start a motor, and they don't give you this, they'll give you a class. They give you what they call full load current. It's rated in amps. But that's how much current the motor will pull if it's running at its rated horsepower. The start current on a motor is 6 to 8 times the full load current. So you're at a plant like US Steel and they want to fire up all those motors. You know, when the motor pulls 100 amps when it runs, that means when you try to start it, it would try to pull from 600 to 800 amps. So a lot of times what they'll do is they'll stagger start motors. So you hit a button and the first motor will start, and then what? After a certain amount of time, the second motor will start. After a certain amount of time, the third motor will start. You run into timers in your car, in a new car. What can you do? You know, you get out there and you get out of your car, the dome light comes on. You close the door, dome light stays on. Then after a certain while, it will do what? You'd go off. Well, that's a timer. And we'll look at, so we'll get to timers and counters. Counters are very important in control circuit, because you need to keep up with how much you work, how much you do, how many rejects you make. You know, if you're in a company and you're running products, you need to know exactly what's going on. How much material do you use? You know, how many cars did you have to reject? How many cars did you take? And that kind of stuff. So what we'll do in this class is the furthest we'll get is counters. Now, in advanced PLCs, we'll get into these compared instructions. Now, this is one thing we can't do with electrical motor control. We can't do logic, and we can't do high-level logic, and we can't do compared. We can't say, okay, if this is less than or equal to, if this is greater than or equal to, or less than, then we can't do this with electrical control circuit. But a PLC is not an electrical control circuit. It's a what? It's a computer. And computers can, by George, that's one of the basic commands, is seeing if two things are the same, if they're not the same. And so we can do things with a PLC, advanced stuff that we can't do with motor controls. This class, we can do everything with motor controls. You can buy counters that would count a relay contact for you. But then you got a problem, okay, how am I going to keep up with that information? How am I going to do math with that? Well, see, a PLC would do all the math for you. So not only would we have the ability for it to keep up with the number of entries, we could have it keep up with the number of exits, and then we could subtract the two with a PLC and come up with the amount of rejects, right? So this is where advantage of the PLC is. But what I want to notice, and this is just a standard so this is a circuit. So this is the symbol on a PLC. This is the symbol for a coil. But it's not a real coil. It's a simulated coil. It's inside the computer. And of course, this is, and we don't have push buttons, so we have very few symbols in PLCs. So what I have right here is this is a symbol for a contact. But this is actually a push button somewhere, and we'll talk about that later on. So all your symbols for contacts are the same. We got two contacts. We got what? We got normally open and normally closed. In motor controls, we would identify the type of contact it is. In PLCs, we identify the type of contact it is by this information we provide. You know, see on the top it says N, I, code, and 0. Well, what we're doing is we're identifying what provides that contact. So here, this would be from an input, from a push button hooked up to the PLC, and that's what we'll learn as we go through here. Are we okay? Now in Logic Pro, it does Logic Pro, which is what you have in your lab book. This is a simulator. Which is really cool. So this is a simulator, but no, it looks about the same, right? You see that? So this is basically, so what is this? This right here is a series parallel circuit, right? Now notice the control devices, they're hooked in series, they're hooked in parallel, but that does not mean, that does not make it a series parallel circuit. This is the parallel circuit, right? Understand? And this will be one rung. If you notice what your PLC does for you, it automatically does what for you? It numbers the rungs for you. Now this is controlling a garage door. So what we have here on here is we can simulate I/O, or we can simulate buttons. Does that make sense? So it says, okay, this belongs to an input. This is a button. It's hooked on module 1, and it's the second button. So here's the input, module 1, second button. It's this guy right here. And notice on this, what are we doing? It's simulating. It's not a real push button. And of course, what I would have to do before I can do this is I'm going to have to go online. So now the thing is connected to the emulated PLC. I'm sorry, go online, Rich. Go online. And then what we have to do now is we have to take this program and convert it over to the language that the computer understands. The computer understands a binary language. We call it machine language. But there's no way in the world I could program, well, that's not true. I used to do machine code programming. But it would be almost impossible for the average person to understand a binary language. So what we do is we write programs in what we call a high-level language. And this is the same language we would use in electrical control. And then we run it through a special program called a compiler, which literally takes this and converts it to binary and uploads the binary program into the computer. So what high-level languages do, it allows us to do what? Write programs in a language that's unique to the trade, and then let the compiler make the machine language program for you. So I'm going to come up here, I'm going to download this, and you'll have to do the same thing, even though this is simulated, and then we'll have to switch the PLC to the run mode. Now, some of the PLCs, we switch between program and run, we switch it through software. Some of your PLCs, like the modular PLCs, we got the 504s down there, you got a key that you switch it. So you have to switch it between program and run with the PLC. Or you can put it in remote mode. So I can see what's going to happen now. And what's nice about a PLC, it shows me what's already true. You see that? So it says this button right here is true. So if I come over and press this button right here, see the yellow light come on? So what we can do with a PLC that's real hard to do in motor controls is it helps us troubleshoot for it. So this is telling me that the PLC is seeing that input right there. Now it's going to take a lot more to energize this. But what this does is this has a bunch of simulators on it. So this is the door opening simulator. And so what we're actually seeing here is a simulation of what's going on here. So what this guy does over here is when I come over here and say open the door, so that would be that switch, right? You understand, but this would be in real life. Why are you working? Oh, I got to switch it to run. Let me switch it to run. Okay, so I'm gonna come over and hit open. And you're seeing all this PLC, but you can see these contacts energized and you can actually see what's going on. And we have the ability to stop at any time. We can stop at any time. My computer's running real slow or something. This simulation is running real slow. Or we can do what with it? We can close it. What we're dealing with, though, is we're dealing with very few actually relays. We got a relay running this, and that's about it. All the other stuff is done with programs. Strictly done with programs. Because 90% of the control of that door is nothing but decision making. When is this button pressed? You know, okay, do you want to stop it? Do you want to do this? And all that other kind of stuff. So this is Logic Pro. This is what's neat about Logic Pro. Is you don't have to have a PLC, but you can do what? Simulating. You can't print your diagram. The one you got in your book, you can't print this. You can save it, but you can't print it. And you have to have your DVD, you have to have your CD in your computer when you run the program. That's one of the versions. But like I said, you can license this for, we recommend this to like high schools and stuff that can't afford to buy the PLCs. They can license this for $15. And they support it for 5 years. So this is what you got, this is what you got in your textbook. That's what's written in. Oh, by the way, on breaks, like I said, I know this is a class that goes through lunch, and it needs 4 hours. What we try to do is take a 10-minute break every hour. But what we decided to do, since it goes through lunch, what we're going to do is we'll take 5-minute breaks. So at 11 o'clock, we'll take a 5-minute break. At 12 o'clock, we'll take a 30-minute break. And what can y'all do then? Your lunch. And then we'll take a 5-minute break at 3. So if class meets 4 hours, that means 40 minutes worth of break, and that would be 40 minutes, right? Is that okay with everybody? Yes, no? Huh? Yeah, it's 1. Sorry, I'm thinking about my other thing. So sometimes the brain goes funny. Let's see what else we need to talk about on electricity, and then we'll get into chapter 1. So where's my PowerPoint over here? The ladder diagrams. Pretty simple, right? By the way, in true ladder diagrams, these are called overloads. The problem with motors is that if a motor pulls 6 to 8 times when you start it, then what would happen if you stalled it? It would pull 6 to 8 times. But my overcurrent protection device has to let the motor start. So that means my overcurrent protection device will probably be rated 125% of start current. So what happens if the motor starts? Well, what happens if the motor stalls? Well, it'll just sit there and burn itself up. The overcurrent protection device is set in there so the motor will start, right? You understand that? So what we have is we have special devices that actually sense overcurrent over time, and these are called overloads. So what these overloads do is they look at the current going to the motor, and if it pulls too much current over a certain amount of time, then it'll trip the circuit out. It'll trip the motor out, and we call those overloads. This is the only thing that's allowed in a motor control circuit. This is the only thing allowed between the load and L2. So all your control devices go from L1, they're connected between L1 and the load. Every control device has got to be between L1 and the load. That makes sense? Your loads are going to be connected to your control devices in L2. The only thing allowed over here is overload. So in PLCs, we don't have overloads inside the PLCs. This is done with a big relay that actually controls the motor. So there, in PLC programs, there is nothing allowed between the load and L2. Y'all understand that? So this is a control circuit. Let me pause this. I'll show y'all these things on a real relay. So in the PLC diagram, we're going to have a L1 and an L2. And then what we do is we'd come over here, and I'm going to put a symbol right here. Okay. And then I'm going to come over here, and I'm going to put a right here. And then I'm going to come over here, and on our PLCs, they represent the coils like that. Now, and then I'm going to come over here, and I'm going to give this a name. Now, and I'm going to call it an output. So what this is going to generate an output out of my PLC. So when we was over there at the manufacturing lines, you saw that we had some lights out there. One of them was for inputs, and one of them was for outputs. So we got 2 options on our outputs. We can use one of the PLC outputs, or we can use what we call an internal relay. An internal relay is software. It's not There's no output ever generated to the outside world. But if I said out 2:1, what I've done on my PLC, there's a screw there that's got a wire coming on it, and it's called out 2:1. So what I've done is I've assigned this coil to an output on my PLC. Now out here, I'm gonna come over here and I might put a light, or I might put a relay, right? You understand? So there's no lights inside the PLC. Physical devices are outside the PLC. So what we've got is we've got all these screws. This is getting a little bit into the next chapter, but that's okay. I know it's time for a break, guys. So this is a PLC. And what we have is we have all these screws over here. These are all labeled. These are outs. And then these over here are what? Ins. That makes sense. And I don't know if y'all can see this. We establish a common, and we'll talk about this. Allen Bradleys are pretty neat. And here's the power light, the run light, the run light, the fault light, and it's got a force light on there. We'll talk about that. And then this is where we can do to set up the PLC. That's what we use here. And we also have access to this PLC. We have access to this, and we might have time to get into that on advanced PLCs, where you can make your program display stuff up there that you want to display. This guy runs off 120 volts. We'll talk about that a little bit. And this is our ways we can connect our computer. We can connect it through a Ethernet port, or we can connect it to what Allen Bradley calls a data highway port. All ours down there right now are connected data highway. So you'll see a adapter, we call them dongles, that takes a USB port and it runs through a dongle and converts it over to the data highway port. Even though we could hook them up that way. The two PLCs we predominantly use down there, we use the Allen Bradley 1000s and we use the Allen Bradley 504s. Neither one of those supports Ethernet, and that's one of the reasons why we were trying to adopt this over to these new PLCs. So that way we wouldn't have to buy that dongle and we could hook these things up to more PLCs. Okay, that makes sense? So inputs and outputs. So technically, if I'm going to wire a true push button up to the thing, somehow I'm going to wire it up to the what? Inputs. And then my lights and my relays and stuff like that, I'm going to hook them up to the what? Outputs. That makes sense. And we don't do wiring in this class. You'll do some wiring in advanced PLCs, but you got to a lot of the labs you have to draw the way you would wire them. Now, the PLCs, inside the symbols for the PLCs, we just use normally open contacts, normally closed contacts. We use the relay coils, and then we use a bunch of rectangles to represent timers, counters, and all that other kind of stuff. On the outside, when you draw the diagram for this, then you got to use those symbols for the electrical control devices, right? You understand? So that's where all those symbols right here come into play. Oops. Won't let me. So when you draw the wiring to the PLC, then you're going to use this for a float switch. This is for a pressure switch. This is for a timer switch. Time delay, on delay. Sorry, this is the flow switch. This is the flow switch. So you have in PLCs, you still have, if you're going to wire the PLCs, when you hook up a float switch, then you use the symbol for a float switch on your diagram for the PLC, right? Does that make sense? Okay, guys, y'all take a 5-minute break. I'm gonna have to put me on alarm.